The second thing we want to explore when we're talking about nuclear physics is this concept of nuclear density. So you may have remembered we talked about how, you have a nucleus, right? It's like, real little. It's a little thing. And if we really look at how far apart these electron orbitals, like these electrons orbit very, very far, and even that's not correct. It would be more correct to take a soccer ball, put it in the middle of a soccer field, and think of the farthest seats at the edge of that soccer field, and that's more along the lines of where the electrons orbit relative to the nucleus. Meaning there is a preposterous amount of empty space in atoms, which means since you are made of atoms, you are a preposterous amount of empty space, and so am I. I'm not trying to get personal here. So the point is, you would imagine that if we were able to actually just hone in and focus on only the nucleus, then everything that we see would have orders of magnitude more density. And there are places in the universe where we do just have nuclear density, where we're talking just collections of nuclei or neutrons. For example, a neutron star, which a neutron star that has an escape velocity of the speed of light is what they call a black hole. So really what I'm trying to say is that when you have a star supernova and it just shoots its guts out and electrons get hurled off of the atoms, you lose that atomic structure where these nice, clean atomic orbitals, and you have something that collapses into something that's basically nuclear density. And you may have remembered from either your own knowledge or from a past semester that there's something called an escape velocity, which is the minimum speed I need to jump in order to free myself of the gravity of a planet. Okay, on some place like Earth, it's relatively low, but for a black hole, what makes a black hole is the escape velocity is the speed of light, so that even if light jumps off from the surface of a planet, it can't free itself from that surface. Although it wouldn't be a planet, it would be a black hole. So all of this is to say that what makes that preposterous amount of mass and density required to have an escape velocity that's greater than the speed of light, it's because of this whole idea of nuclear density, and that nuclear density being so much higher than it is for a typical atom because you lose all this empty space. So let's take a look at it. What would be, for example, the nuclear density of just an oxygen nucleus, right? So let's take an oxygen nucleus, and there's like atomic mass number of 18. So imagine you have just 1, 2, 3, 4, 5, 6, 7, 18 particles. I don't even know if that's 18. I'm not going to waste the time counting it, but you get the idea. And then you have electrons surrounding it. But let's just look at the nucleus. What is going to be the actual nuclear density of just this nucleus right here, right? Which is basically a sphere with radius r, right? Okay, so first things first. If we want to find the density of anything, right, it's going to be the mass divided by the volume. And we know the mass of this because it's 18. Confirming, yep. 18 is the atomic mass number of oxygen. And so it's 18 times the mass of each of those particles. And we know that 1.67 times 10 to the minus 27 kilograms is the mass of each of those particles, right? And that's got to be all divided by 4/3 pi r cubed, which is the volume of a sphere, right? A volume of a sphere is 4/3 pi r cubed. So we can get the density of an oxygen nucleus if we can just find out what r is. Okay? Well, it turns out, as you can see from this slide, there is a handy-dandy formula that as long as you have the atomic mass number, you can always get the radius of a nucleus. Okay? So the radius of any nucleus, Rn, the radius of the nucleus, is going to be equal to about, this is an approximation, you can't nail this down perfectly, but a solid approximation is 1.2 times 10 to the minus 15 meters times the atomic mass number to the 1/3 power. Okay? And so if I put in the atomic mass number of 18 in for R, I actually get an R value of 3 times 10 to the minus 15 meters. Okay? So, in other words, the radius of an oxygen atom is this ridiculously tiny number, 3 times 10 to the minus 15 meters. Okay? And if I go ahead and I take that number, and I encourage you to do this with me, and put it in for the radius, then I can get my density of the nucleus of an oxygen atom. I put that in, and I get, wow, 2.7 times 10 to the 16 kilograms per meters cubed. Do you have any idea how dense that is? So in one little box, a meter cubed, right? Just imagine a box, a meter cubed. I would have 2.7 with 16 zeros over it, kilogram weight in that box. That is a preposterous amount of weight. And to wrap your head around that kind of weight, okay, I want you to look at a different question. And that question is part B here. It says, how much would a teaspoon of oxygen atoms weigh in pounds? Okay? How much would it weigh in pounds? So here's the deal. We are going to do the classic, we're going to do the classic density formula in order to solve this problem. So I'm going to go ahead and erase this right here. Okay? And remember, density is mass per volume, right? This time we want to find the mass and then use that to turn into pounds. Okay? So let's say that mass is equal to rho times volume, right? So if I want to find the mass of the oxygen nuclei in a teaspoon, then I want to take that density, the density of the nuclei, which is just 2.7 times 10 to the 16 kilograms per meters cubed, times the volume of a teaspoon. Okay, so I'm not going to make you look this up, but I looked it up for you. The volume of a teaspoon is 5 times 10 to the minus 6 meters cubed. Very, very tiny, right? Okay, well, let's go ahead and multiply this. Meters cubed cancels. I get a mass of 1.3 times 10 to the 11 kilograms. Okay, and then this question wanted it in pounds. Okay, so do you remember the conversion between kilograms and pounds? So remember, 1 kilogram is equal to 2.2 pounds, right? So, I mean, basically, you're just taking this number and multiplying by 2.2, which ends up being 2.6 times 10 to the 11 pounds. That is huge, and for like relative comparison, that many pounds is about, actually more than, the mass of all the Great Lakes in the United States of America. So if you add up all the Great Lakes all together, this teaspoon of nuclei weigh as much as all the mass of those Great Lakes, which is preposterous to me and amazing, and gives you a little sense of why it is that black holes can actually form, because their density is such that a teaspoon of black hole weighs as much as the largest lakes in the North American continent. So I hope that gives you some sense of comparison and some sense of awe and wonder. And when we get back, we're going to talk about what actually holds this together.